Today's talk of Semiva on spectral algebraic geometry is by Krishna Kumar, and it is on locally Noetherian stacks. Please, Krishna.
Thank you, Philip, for the presentation. So, as you mentioned, the talk for today is going to be about locally Noetherian stacks, in particular locally Noetherian quasi-geometric stacks. So the running time I've mentioned is to be medium, which is supposed to mean that it's going to be lesser than the previous talk that I presented, right? And yeah, just like always, if there's any questions or something to be clarified, just raise your voices so that we can go through it. All right. So I would like to go through the flow of the talk to set up the stage. So first, we are going to see some definitions of what we have already seen in previous talks. For example, something about quasi-geometric stacks and just an intuition about what they are. That would be good for understanding the specialization of what we are going to consider, right? And then, so there is this notion of perfect stacks that is very sort of natural thing to look about in any category, like a perfect objects. So this, I think that this wasn't defined in the previous talk, so we will have a short crash course on this thing so that it sets up a good base for the locally Noetherian case. And in particular, in this sense, in this topic, we'll see what are almost perfect objects, and we'll see the definition of when a stack has store amplitude less than or equal to a given integer. And then we'll come back to seeing the basic definitions of locally Noetherian or Noetherian stacks and give some basic examples on this. So for example, we'll see that the classifying stack that we have seen in the previous talks sets us a nice example, one of the basic examples to study. And there is this object FGLR, LFR, which I'm not going to say what it is. Let's keep that suspense till the end. But it's a very exploited object, and it's a very rich object to study. And also in this case, we'll look upon some kind of nice characterizations of which kind of stacks can be Noetherian, depending so characterizing Noetherian stacks by seeing if the pullback is a finitely generated module and things like that. So which is a very interesting thing to see. And then we'll end up this talk with giving the statement of Tannaka duality for the setting of locally Noetherian stacks. And then we'll also give a speculation of what happens if we just weaker the assumption a bit. Okay. So I would like to call this section as a base camp for Noetherian stacks, where we learn the things that we need for the talk. So as we've seen in the talks before, a quasi-geometric stack is so it's obtained more roughly speaking, it is obtained by the following way. So you take an affine spectral algebraic space, spec of A being any E infinity ring, right? And then you consider the group which is flat and quasi-affine, suitably over a field defined over a field K. So and then take the stack theoretic quotient of the space spec A by this G, and then the stack theoretic quotient, and the quotient is to be understood with respect to the FPQC topology. So the object that we get is called the quasi-geometric stack. So more precisely, what we have seen is it was defined as a functor from this category of commutative algebra objects which are connective and to the category of spaces. So this hat means that it need not be necessarily small, although all the setting that we are considering in the talk so far has been small, all have mapping spaces to be small objects. So such a functor has to satisfy descent with respect to FPQC topology, and the diagonal morphism, as we have seen, has to be quasi-affine. This means that if we have any other object and we take the pullback with respect to this object, what we get here has to be quasi-affine object. So this is something that we have seen. And then the third condition is that there exists a connective E infinity ring A with a faithfully flat map into the space into the stack that we are considering. So faithfully flat for us means it's flat and surjective. So as a first example, we have seen that the classifying stack is of course a quasi-geometric stack. So when G is a affine group scheme defined over a given field, right? So in particular, all quasi-compact spaces give a first nice examples of quasi-geometric stacks. So and then what is a geometric stack? So it is a quasi-geometric stack, except that you just have to so this is a very rough idea of what it means to be, right? So you just replace this quasi-affineness by affine condition. So for example, you just change the diagonal morphism to be affine, and then what we get is a geometric stack, as we will also see in the upcoming talks. right? So, and then we have this Tannaka duality statement in each of these cases. So, which roughly states when does a pullback behave like a equivalence of categories, right? So, in particular, there is this statement that we are specifically considering the essential image, and we are sort of analyzing what this image can tell us about the pullback functor. So this pullback functor is it's defined between the quasi-coherent objects of x and y. So this we have seen that it is spanned by all those functors that preserves these three properties. In particular, we have small colimits. It has to preserve small colimits, connective objects, and flat objects. So one nice setting of locally Noetherian hypothesis is that we can relax this a bit in a sense that if we already assume locally Noetherian, the condition C is automatic. So it's just taken for granted by just taking that the stack is satisfies locally Noetherianness. So this is partially because this idea of functors preserving flatness is something that has to do with perfectness. So if you have a perfect object, they sort of preserve this flatness. And so we will see that Noetherian stacks are something that can be approximated by perfect objects, which is called almost perfect objects. Okay, so well, what is a perfect object? We haven't studied that yet. So we'll quickly see what does it mean to be perfect. So a perfect object, roughly, to have a good holistic idea, it has to be thought of as a compact object of the category that we have been talking about. So it's the commutative algebra objects of connective objects, commutative algebra category of connective objects. So just take the compact object of this category, that is what we would call a perfect stack. So the loose definition would be, so given a functor, we call it perfect if the induced map with respect to the end completion, it has to be an equivalence of categories. So incompletion was something that we already talked about in my previous talk. So in particular, we have seen that the category of spectra is obtained by incompleting something, right? And what was that something? That something was the perfect object of the category of spectra. And so just to recap it a bit, so the incompletion is a process of formally adding arbitrary filtered colimits so that the category is like a localization process in which you add this kind of colimits so that that the perfect objects can be identified using this property. So in particular, perfect objects are invariant under incompletion. That's what I mean. So essentially, every category that we know is obtained by incompleting its perfect objects. For example, if you look at the category of set, then the finite sets are perfect objects of this category, and in completing this, we get the category of sets. So for groups, it is finitely presented groups, and for chain complexes, it is what we call perfect complexes. You just incomplete it and get back the category of chain complexes. And for spectra, it is the category of finite spectra. And for the category that we're considering today, this would be perfect stacks. So this is where the perfectness sits inside, and it's a very, very very nice thing to see about a category, and it's one of the best properties that a category can have. So in this sense, perfect stacks, they supply enough compact objects to the category of quasi-coherent sheaves on a given stack. So so once we have this functor, when do we call it to be perfect? It is perfect if, first of all, it is a quasi-geometric stack. And then the structure sheaf associated with this X has to be a compact object of the quasi-coherent category of quasi-coherent sheaves on X. And then for any such sheaf, we should be able to express it as a filtered colimits of all perfect objects. So if a functor satisfies these properties, we say it's a perfect functor, meaning that it's a perfect object. So some quick examples would be if G is any affine algebraic group defined over a field K of characteristic 0, then we can take the stack theoretic quotient, and what we get is a classifying stack again. So the BG that we have seen throughout this seminar is a perfect object. And more generally, what you can do is you can take X to be a quasi-projective K scheme and then take this stack theoretic quotient, and what we get is also perfect, right? So in fact, what we can say is if an given object is perfect, if and only if you take the category of quasi-coherent sheaves on it, then this category has to be compactly generated with the structure sheaf sitting inside the compact component somehow of this QCoh of this category. So why are we talking about perfect stacks? Because to utilize the fullness of locally Noetherian stacks, we have to sort of know what are perfect stacks, but then we have to also relax this a bit so as to utilize it more efficiently. So that would be the notion of almost perfect sheaves. So almost perfect sheaves are something that is level-wise perfect. So they're not perfect as when you see it as a whole spectrum, but at each stage, there is a stage at which it starts to be perfect. Right? So let's start with the connective associative ring spectrum. So E1 is also denoted as A infinity in literature. So A is standing for associativity. So associative ring spectrum is something like a commutative ring spectrum, except that it's not commutative. It's just associative. So we say a left R module M is almost perfect if we can find an integer k such that this module that we consider is sitting inside this left R module after some stage, after this stage k, and M has to be almost compact as an object of this left module after the stage k. So just as I explained before, they are like level-wise perfect. After a stage, they start becoming perfect, and these are very, very useful to sort of study some special cases as we will see. So just for the notations, we denote the category of almost perfect sheaves by this notation here. And then if you have a compactly generated infinity category C, and then we can talk about almost compact objects. And it is also defined level-wise. So an object is almost compact if you take the truncation and nth truncation of this C. This has to be a compact object in the nth truncated category correspondingly. So every compact object is almost compact just by definition. And it's also an interesting exercise to find out what are almost compact objects which are not compact. So this would be a good exercise to work out. And then just for completeness, I'll also spell out this definition of Tor amplitude. So once again, associative link spectrum, take a module, left R module, and then when do we say this this module has a Tor amplitude less than or equal to n? So we have Tor. It means that there's some torsion component and it has to be killed somehow, right? This is the intuition we have, and that's the case here as well. So for every discrete right R module n, so you consider the homotopy groups in the derived tensor product. So and apply this pi I to this tensor product, and this has to vanish for every I greater than n. So if this happens, we say that so this n is what we have it here. So the module has Tor amplitude n if sort of this vanishes for everything after this stage. So what do we have next is we say that M has a finite Tor amplitude if this n is if there is a fixed integer n such that and n has to be finite such that this Tor amplitude is less than this given number. Now this is a very useful fact. This is from high algebra that we would use to prove something in the proportion that we will see is something. If you have a connective left R module which has Tor amplitude less than or equal to 0, then it has to be a flat object. So this could be seen, but this one is a very crucial thing, and this helps us to prove something about the Tannaka duality statement. And just as a last definition, we have something called as a locally almost a finite presentation. So a stack is such if in every affine neighborhood that is locally, we have this criteria here. So sort of like for every k, take any filtered colimit filtered directed system, meaning colimit diagram with the index I. So you just go to the kth truncated category, and then the natural map has to be a weak equivalence. So if this happens, we say that a given geometric stack is locally almost a finite presentation. All right. And so a stack throughout would mean that it's a quasi-geometric stack, and S would denote the infinity category of spaces, anima or homotopy types, whatever you prefer. So why are we considering this idea of locally Noetherianness? Because locally Noetherianness is sort of like a finiteness condition, just like how perfect stacks was. So they are very closely associated with the perfect object of the category concerned. We have seen this already. And so Tannaka duality, if we restrict it to the case of locally Noetherian stacks, they take much simpler form compared to the other statements that you have seen. All right, here's the first definition, official definition of the day, which is a quasi-geometric stack is locally Noetherian if there is a faithfully flat map from spec R to X, where R is supposed to be a Noetherian E-infinity ring. So this is crucial. So it's just two data having faithfully flat and having this R to be Noetherian E-infinity. So again, a quick example would be the classifying stack. Provided that the R you take as Noetherian commutative, usual commutative ring, and then G has to be a flat quasi-affine group over this scheme, and then take the usual stack theoretic quotient. What we get is locally Noetherian. So there's something to be careful of here. So X is Noetherian just by the definition means that we have this faithfully flat map with R being Noetherian. So this is by definition. But there are maps which are faithfully flat, but R need not be Noetherian E-infinity ring. So this is very crucial. And in fact, as it turns out that this is almost never the case. So this would never happen actually. And this would happen if and only if so we're going to see the if and only if part. So how to resolve this is, so you got to assume some kind of finiteness condition on F, so as to have this to be assertive. So this gives rise to a Noetherian stack. All right. So we'll see that we now see what does this finiteness condition exactly means, right? So we would have already guessed it. So if X is a locally Noetherian quasi-geometric stack, and we have this map here, and if we assume this F to be locally almost a finite presentation, then R is Noetherian. So this is the crucial fact that we need. So I would quickly go through the proof. So if you have some doubts regarding the statements and something said before, you can ask me. All right. So we'll go through the proof now. So we have that X is locally Noetherian. So by definition, we can choose a faithfully flat map G from spec A to X, and A has to be Noetherian. This is just by the definition. And then we are going to form this pullback using these maps that we have defined. So we have this F here, and this is which is given, and G that we have chosen. So just form this pullback, and we see that Y has to be a quasi-affine spectral algebraic space, and this is a matter of observation. And from the definition of being an algebraic space, we know that it admits étale presentation. So meaning that it has an étale surjection. So call it spec B to Y. So we are going to play with this surjection. In particular, we are going to play with this map to show that this is actually Noetherian. That's the whole idea. So we also have the assumption that X is locally almost a finite presentation. Sorry. So we have this E-infinity ring B is almost a finite presentation. So this is just going back and forth from the module and the spectral space and the underlying ring correspondence. So this actually means that B is actually Noetherian over A. And now we have to show that R is also Noetherian. So we use a very strong lemma from higher algebra, which states that for a faithfully flat map, C to D, C being Noetherian suffices to show that D is also Noetherian. So in particular, G that we have is faithfully flat. We have chosen so, right? And the ring B is faithfully flat over R. This is because G is faithfully flat. So this is the correspondence that I mentioned. And then we sort of use the lemma to show that so this is faithfully flat, and we have that this is Noetherian. So this being faithfully flat implies that B is a Noetherian, and by the lemma, what we know is this being Noetherian gives that R is also Noetherian. Okay. So, and then we'll see. We'll now go to the definition of Noetherian stacks, which is in some case like taking a smaller class so that this is already satisfied. So a quasi-geometric stack is Noetherian if there is a faithfully flat map from spec R to X, and F is locally almost of finite presentation. So this There's no surprise here. So a quick example would again be BG, but then consider G to be of finite presentation. So so earlier we had locally of finite presentation, just replace that by finite presentation. We have a good candidate here. Okay, so of course there is a difference between locally Noetherian and Noetherian, right? Or else we wouldn't study two notions. And this would be illuminated by giving the following example. So for those of you who haven't seen this gadget called formal group laws that I'm going to give a quick glimpse about. So a formal group law is one could think of it as a formal power series, which is sort of like, which acts like a multiplication map for Lie groups, I would say. So for any given commutative ring R, we can build this formal group law over R. So in particular, one-dimensional formal group law. So it can be, there are n-dimensional. So I'll just stick on to one dimension now. So one-dimensional formal group law is a formal power series of this form with the coefficients from the ring R, which satisfies these three properties. So it has to be unital. So it's just what's written on the screen. So it's just you have to take x0 to x, and then you should be able to easily swap between brackets, which is associativity, and then you have to be able to swap objects, so which is commutativity. So a very basic example of formal group law would be the additive formal group law, and these are very important objects. So it's just by ignoring all the higher powers, you just take x plus y, and it satisfies all these properties. We can quickly verify. And then it is actually an example of formal group law. So attached to this formal group law, there's this notion of height, and it's a very good invariant. So in particular, height is like roughly defined as a power of the multiplication by P map. So P being the prime. So as a convention, if we have the map to be just 0, so this trivially satisfies the axioms that we want to show. So by convention, the height is taken to be infinite. And every additive formal group law has height infinite. So this is because the pth power map is the only possible map is just 0, because there's no other map that makes sense in this definition here. So depending upon the base field, there are two different things that we can talk about. So if the characteristic of the field is 0, then it's a theorem that every formal group law is isomorphic to an additive formal group law. So the height has to be infinite in this case. So the interesting case is when the field is of positive characteristic. So the height in this case is just the integer appearing in the first non-zero term. So why are we talking about all this is because this gives a good example of what we are trying to sort of contrast, right? So one can consider the moduli stack, which is this thing that we've seen before, which is FGL of R. This is not locally Noetherian, but it has an open substack, which is sort of conceptualized to classify all the formal group laws up to height n, so over the corresponding p-local ring. So this guy it's sub-object of this pullback here. So one can show that this is locally Noetherian, but it is not Noetherian. So this gives us a rich set of examples that shows us the difference between being locally Noetherian and Noetherian. Okay, so before going on to the next big statement, so let's recall a few things. So throughout, heart actually means like, so we are dealing with the spectral objects, and taking heart takes us back to where things actually make sense in some sense. Like we go to the one categorical underlying categories, right? So this category of coherent sheaves is generated by all those quasi-coherent sheaves that are spanned by this almost perfect objects. So if you have a locally Noetherian quasi-geometric stack, it determines the map. It determines a faithfully flat map. This is from the definition, and then this induces a pullback, natural pullback, and then take the heart of it. So if we have spec of A, the associated quasi-coherent sheaves are they correspond to the modules over A, right? So then we have this nice characterization that an object in QCoh, it actually belongs to the coherent object if and only if you go to the pullback. This is one of the nicest statements where we use pullback to make tangible results. So you can sort of go back and forth, right? You just take the pullback, and it has to be a finitely generated A module. Right? So we're going to use this fact again in what's upcoming. So we now use these that we have developed to show that this category of quasi-coherent sheaves, which are with connective objects, they have many almost perfect objects. And so there is this definition here because this category is a pre-stable infinity category, and then we're going to use some of these properties. Like, I mean, it's not going to be explicit, but it's somehow buried inside. So I would like to have this for completeness, but you don't have to worry much about it. And then I would like to call this as crux 1 because this is one of the first big results that you're going to see today. So for a locally Noetherian quasi-geometric stack, the connective component, connective objects of the quasi-coherent sheaves on it is actually locally Noetherian, and then an object is Noetherian if and only if it belongs to if it belongs to the coherent sheaves on X. So yeah, just to keep the sanity intact, I'm not going to sort of go through every single line and as it's described in the book, but I'm just going to give a sketch of it. Right? So first you're going to prove the statement 2, and then using this as a consequence, we'll see the statement 1 holds with some additional statements. So the first step is to sort of have this kind of characterization where every coherent object, say if you have a sheaf in QoH R, then it is a Noetherian object of this one. So this is like the very first step. And the second step is to sort of show that every object in QCoh admits a filtration by Noetherian subobject. So we're going to like reduce the whole object being quasi-coherent to taking the colimits with each of the colimits Noetherian. And then the third step would be sort of to show that if we have a coherent sheaf on X, then it is a compact object of the connective quasi-coherent sheaf truncated to this degree n. Right? Okay, so to prove the first step, so we have to show something is Noetherian, right? So right from the commutative algebra, what the tool that we have is this idea of ascending chain condition. So it's a wish to show that this satisfies this ascending criteria. So that is like you just take the ascending sequence of sheaves. So it is an object here. And then we have to show that if it eventually stabilizes. So there is this Fn, this n there, and which sort of stabilizes after what comes up next to it. So X is locally Noetherian, this is given, and you can choose a faithfully flat map F from spec A to X, where A being Noetherian in infinity. And then we can see that the pullback functor, the natural pullback functor is T exact. So I'm not going to explain what is T exact means because it's I'm not sure if we have described it, but the idea is like this category of quasi-coherent sheaves on X forms a triangulated category, and the triangulated category comes equipped with the T structure that sort of satisfies some nice axioms. And then this pullback functor is actually exact with respect to that functor which has this triangulated category. So you can identify this pullback for each n. You can identify this pullback with the sub-object of the module. So this was exactly this was exactly as in this case we have here. And so once we have identified this pullback as a sub-object here, then the ascending sequence we had sort of translates to ascending sequence in just A modules, like the category of A modules. And so a sheaf in a coherent sheaf is same as saying that the pullback is actually a finitely generated module over pi naught of A. So A is Noetherian infinity, meaning that pi naught of A is also Noetherian, like pi naught of A is a Noetherian commutative ring as discrete. And so that's what it's mentioned here. And so what happens is like we have sort of reduced the ascending chain from the original space to the space of A modules, and this has to stabilize. This is because of the fact that's mentioned here. And then we use the fact that this pullback is actually a conservative functor to show that, so conservative is something that if we have some isomorphism here, then it has to be an isomorphism here as well. So this sort of gives us what we want, it stabilizes. So to go to step 2, what we have is we have to show that every F here has to be given as a colimit of Noetherian subobjects. So what we do is you just take the pullback and call it G, and it can be equipped with a discrete module structure over this pi naught of A. So you can write G as a filtered colimits of limit of this G beta, where each G beta is a sub-object, and being a sub-object of G actually corresponds to having a finitely generated module over pi naught of A. So then we see that we have this direct image functor, and it is left T exact. Again, this is actually observation from higher algebra. So we have this identification that the push forward of this G beta truncated to this degree can be identified with this push forward of the whole object. So for each index beta, so we can sort of denote this F beta to be the sub object, which is given by this pullback here. So so the push forward preserves small colimits. So as a consequence, we can sort of consider the push forward of G with respect to its components. So moreover, what we have is the T structure of the quasi-coherent sheaves on X. It is compatible with the filtered colimits. And so we have a canonical equivalence of this form. So altogether, putting back this statement and this statement, what we have is F can be expressed as colimit of F betas. So now it's enough to show that F betas are actually Noetherian. They actually belong to this coherent component. So for that, we have to show that the pullback is actually finitely generated over pi naught of A. So this bridge is something that we have been crossing so many times in this single talk, and also in the previous talks, also in the talks upcoming. So this is a very crucial sort of correspondence. And by construction, what you have explained, we have two commutative diagrams here, and then yeah. So now what you have to do is do some kind of diagram chase to obtain that each of this G beta is actually finitely generated module over pi naught of A. And pi naught of A is Noetherian because A was Noetherian. And then, so because of this, we can see that the pullback corresponds to a finitely generated module over pi naught of A. So what it says is this exactly, that F beta actually belongs to the coherent component of the valued on X. So in order to sum up, we can sort of see that if F is a coherent sheaf, which is Noetherian, as we have already assumed, then F is isomorphic to this limit. But this means that there should be some beta such that F is isomorphic to exactly this component, and F beta is actually in the coherent component. So this proves what we need for the second case. And then for the first case, to verify that, we're going to use step 1 and 2. Which in essence says that every quasi-coherent sheaf is a colimit of Noetherian subobjects, right? So this actually means that the category itself is locally Noetherian. And now we show that the connective objects is actually locally Noetherian. And so this is the normal abelian category, and this would be the infinity category. So equivalently, it suffices to show that every object in this category is compact object. So in particular, perfect object of this truncated category. So by definition, what we have is the construction of sending G to the representable mapping space. This determines a functor, forgetful functor from the category of quasi-coherent sheaves to S, the category of spaces. So this commutes with filtered colimits. And so going through briefly, what one does after this is once we have this stat, consider this check nerve construction. And this check nerve construction comes with a totalization, which is like it can be considered as a dualization. It's a dual process of taking geometric realization, right? So yeah, this is just observing that taking this check nerve and observing each of the x ends in the nerve is a quasi-affine Deligne-Mumford spectral Deligne-Mumford stack. And then F is fully faithful actually implies that we have an equivalence of categories. So you can identify this functor with this functor, and we can sort of work totally with this functor now. So now to show that, we actually have to show this restricted to the connective object is actually Noetherian. So it is enough to show that this restriction is actually equivalence, and with this we know is already satisfies the property what we want. And just to sum it up, we're going to use the notion of almost perfectness of each of these xm's, again level-wise, to show the step 3 that we moved. All right. So a quick digression here before going on to the next big statement is the concept of internal home sheaves. So if you have a quasi-geometric stack, we have seen that the infinity category is presentable, it is monoidal with respect to this tensor product, and it is symmetric, and it is closed. So the closed is actually important. So being closed means it has its own home sheaves, right? Many of the nicest categories we know are closed. So in particular, for any pair of objects, we can define a mapping space that actually belongs to the category itself. And it is defined by the usual universal property, which I'm not going to explain, but have this evaluation map here, and this map has to be an homotopy equivalence. So this is what we have seen. So essentially, this is So this is exactly what people write, this capital home and small home. So this home would be like the usual maps, and this would be an object which acts as a home object, but it sits inside the category itself. So to digest the whole context, so take X to be spec of A, just affine case. So in this case, any sheaf, quasi-coherent sheaf, actually corresponds to A modules, M and N. So here the internal home would exactly be the home of two modules, I would say. So it's home between M and N, or as a module. And so what is the importance of almost perfectness in the whole talk today? So you have a morphism of quasi-geometric stack, which is quasi-affine and flat. And you take a pair, and then this canonical map that is obtained by the pullback. It is usually not an equivalence. It is an equivalence if and only if this sheaf has to be almost perfect, and this has to be truncated to this degree here. So in this case, like almost perfectness gives a nice class. It adds to the more equivalences to the category that we have. All right, so this would be our last sort of important step to concluding that what is Tannaka duality for locally Noetherian setting. So this I would like to call crux 2. So, and if there are any questions or something to be clarified, you could sort of raise up your questions. All right, so you have this. So let's go to the statement first. So if you take two functors from this category of commutative algebra objects which are connective to the category of spaces, and assume that X is locally Noetherian. It's geometric, quasi-geometric stack. I'll explain why this is difference. And then the construction of sending this F to its pullback, it actually determines a fully faithful embedding. This is exactly the map that we have been seeing for many weeks. Right, so essentially nothing changes here. We have just added this hypothesis, and what happens is in the essential image. So the essential image is spanned by those functors, which preserve small colimits, connective objects, and if we consider quasi-geometric stacks, it also preserves almost perfect objects. Right. So we'll only prove the case when X is taken to be geometric, and for quasi-geometric, we'll sort of just state that the following lemma will sort of be the main idea of the whole proof somehow, because today I designed the talk so as to have more emphasis on the ideas than the proofs, which I guess is the more holistic point of this whole seminar. So we'll only prove this case, right? So to prove crux 2, what we need is the following two things. So we need this lemma, and we would also need this proposition. So let's go through the lemma. So I would like to call it crux lemma, which states that if we have a zero truncated quasi-geometric stack, and if R is a connective commutative ring spectrum, and define a functor from the quasi-coherent sheaves to the modules, preserving small colimits and connective objects. So now if we consider a morphism in this category from F and F prime, so assume F to be almost perfect and F prime to have Tor amplitude less than or equal to 0. So then what we can say is for any module M truncated up to 0, so the natural induced map by taking the tensor product, this has to factor through an object of this form. So it has to factor through an object from this category. So this is very crucial. we'll prove the following proposition, which would sort of give an idea of what would happen in the geometric case. So again, consider two functors and assume that the functor between the associated quasi-coherent categories is symmetric monoidal and it preserves small colimits and connective objects. Then, if X is locally Noetherian and take any quasi-coherent sheaf which has Tor amplitude less than or equal to 0, then the image of under this functor F also has Tor amplitude less than or equal to 0. So just a spoiler, this would already tell us this functor preserves flatness. So that's the whole idea of using this proposition. So without a lot of generality, we can assume that Y is an affine object. So in particular, take the corresponding category of quasi-coherent sheaves is a category of R modules. So for a discrete R module M, we want to show that this tensor actually belongs to this category. So I mean, by definition, being Tor amplitude less than or equal to 0 means that it actually belongs to this. So take the tensor and take the pi I, it has to vanish. So in other words, it has to be in this category up to this truncation. So set R prime to be the image of the structure sheaf, the connected component of structure sheaf. So F preserves connective objects. This is our assumption. So then we have the natural unit map between OX and the connected component of OX. Right? So by virtue of being preserving connective objects, if this map has one connective fiber, then it means that this F has to induce an isomorphism on the connected component. This is very crucial. And take the zero truncation of X, and we identify this truncation as a functor via this V, just this notation. And so this map F that we have before, it induces a map on this zero truncated version. So what we are trying to do is like sort of reducing the problem of the whole object to just analyzing the zero truncated object, and passing between these two categories is allowed because it preserves connective objects. So we're just taking the pi naught component and working with it. F induces this map here between the X prime, and it can be identified with the module over this ring here, and send it back to R prime. So as a matter of fact, we can see that F prime preserves small colimits and connective objects. So what this tells us is you take the tensor product and it has to be isomorphic to the tensor product of the zero truncated version. Right, so that's what I define. You just reduce everything to the zero truncated case by replacing X to X prime, F to F prime, and F to the pullback of via this zero truncation function. Right. So X is locally Noetherian from the hypothesis, and from crux 1, the proposition we proved earlier. What we can sort of show is we have the connective component of this quasi-coherent sheaf is locally Noetherian. This was proven before. So hence you can express this sheaf as a colimit of almost perfect sheaves. This is also clear. And if F preserves colimits, what we have is taking the tensor product is actually taking the tensor product with respect to each of the component and taking out limit. So in particular, if we have an element of pi n of this ring here, take the nth homotopy, it has to lie in the image of this map. This is because of this equivalence we have here for some alpha. But then these maps has to factor through the so by this lemma, by the lemma that we proved, what we mean is a map of this form has to factor through an object here, and factoring to that object there exactly means the homotopy nth homotopy vanishes for n less than or equal to 0, and this is what we have to show. And what would be important is the corollary of the statement, which says that with the setting as above, if X is a locally Noetherian quasi-geometric stack, then take the functor from quasi-coherent objects on X to Y. So it carries flat objects to flat objects. So what is the claim is if you have any quasi-coherent sheaf, if it is flat, then F is both connective and has Tor amplitude less than or equal to 0. So we can use the proposition, the crux proposition you've stated above. This would be crux 2 to show that this image has Tor amplitude less than or equal to 0. And what we have right now is tar of this one less than or equal to 0, and it preserves connective objects. This means that f of f has to be flat. So this is also pretty much related to this fact that I've mentioned before. And essentially the proof of the case when X is geometric would be to use the proof of Tannaka duality for geometric stacks, which I think we would see in the next upcoming talks. But this is sort of the crux that we have seen, and I use this corollary to sort of sum up with the idea. So just to give a overview of what happens for almost perfect objects, from crux 1, what we know is this category of quasi-coherent sheaves on X. It contains many almost perfect objects, like almost compact objects. So we can restate the Tannaka duality using almost perfect sheaves. The statement would exactly be the same, where we would just replace the category of quasi-coherent sheaves by its subcategory of almost perfect sheaves, right? And it determines a fully faithful embedding. So this map has an essential image which is spanned by this kind of almost perfect objects, which are exact, and it preserves connective objects. So we see that for almost perfect sheaves, we have a very similar statement, and reducing to almost perfect sheaves gives a more hold on what we have to sort of prove. And so just to give a heads up for the next talk, so it's about Tannaka duality for spectral algebraic spaces, and I suppose that there's a lot of interesting application, including the Sayre criteria on affineness and things like that. So I'd be very much interested to look forward to the talk. So I would stop here. Thank you.
Okay, thank you, Krishna, for the talk. Is there any question? Okay, that does not seem to be the case. So let's thank Krishna again. And see you next time. Bye-bye.
Bye-bye.